Good morning, everybody, and thank you for joining us. Just a few quick housekeeping things. This session will be being recorded, so please keep your microphones and cameras off. If you have a question that you'd like to ask, please drop it in the chat as we're presenting, and we will review them as we go. We'll kick off now. So welcome everyone to the wrap up of the final Western Power Distribution Data Science Challenge of the series. The agenda for today is WPD will give a quick introduction to the background and the context. I will then cover the recap of what Challenge 3 was about and the goals the problem structure and the goals we're trying to achieve with it. And then we'll have presentations from the top 3 teams, followed by a summary from Steve of what we've learned from all of the challenges combined and some of the next steps coming out of that. So without further ado, let me hand over to Liam from WPD.
Thanks, Sam. So yeah, thanks and good morning, everyone. So yeah, in terms of the aim of these challenges is around us seeing what other people can do with our data, I suppose, is the main objective. So like that's mentioned here, demonstrate the value of making unique data sets available. Now we've currently got, I think, in the region of 1,500 resources available on our connected data portal, which I know has been pivotal in the data science challenges that have been conducted. And for us, it's about highlighting some of the data-driven challenges facing us as DNOs. From discussions with my transmission colleagues yesterday, they're also facing the same challenges as well. And the other aspect that I think is quite good with the open data aspect is developing that community. And I know we're focusing on the DNO element here, but the wider, or bit of a buzzword at the moment, the whole system as well is another kind of avenue we'll look at, I think, going forward. And I think for some of the main parameters we want to get out of it is what having a fresh look at the data and what you can do with it. And off the back of that, we can then bring that internally and use that as to benchmark some of our data. So overall, I've been super excited looking at what comes out of these data science challenges, and we're hoping to push some of the code that you guys have painstakingly been writing over the past couple of weeks to our GitHub repos, so or link them at least, so other people can have a look and see what amazing work you've done and hopefully apply it to their own data sets. So yeah, that kind of covers the welcome and aim. Sam, I hope that's okay.
Thanks, Liam.
No problem.
So let me give you an overview of Challenge 3. So as we've kind of seen in the UK and across the world, there's kind of increasing amounts of low carbon technology and distributed generation. And that puts a lot of strain on the distribution network. And that leads to the need to kind of monitor the network more intensely and kind of understand power flows within the whole hierarchy of the network. But the challenge with that is sometimes the monitoring or data collection fails, or there are transmission errors, or for many different reasons, there are gaps in the data. And so this challenge was about how can you estimate the missing data within the kind of distribution network hierarchy for various different types of monitoring data failure. So this is an example of the network hierarchy. You have the grid supply point, which is kind of like a high voltage substation. And below that, you have a number of bulk supply points. And underneath those, you have primary substations, which are kind of lower voltage substations. And the goal was kind of given demand data from each of these substations with various combinations of missingness, how could you fill in those missing gaps? So there were 8 different scenarios covering different types of missing. So scenario 1, where all the data was missing. Scenario 2, where the grid supply point and all the bulk supply points were missing, but the primaries were present. And then various other kind of combinations of missing that in theory allow you could use different approaches to the hierarchy to solve and to kind of fill in that missing data. In order to score and benchmark this problem, the thing that we focused on really was the root mean square error, but the coefficient of variation of that, so kind of normalized for the mean of each time series, so that essentially you have primary the ability to predict a primary substation where you've got a relatively small demand is just as important as the ability to predict the whole grid supply point. So it's normalized for each substation, and then we normalized that and kind of like benchmark to a benchmark which was based on assuming that the data today was the same as the data the day before. So kind of a very simple benchmark that could be used, but that should also kind of in theory be relatively easy to improve on. The data that we provided was 2 years worth of data for the Iron Acton grid supply point, with 9 bulk supply points and 29 primary substations underneath that. And all of that was released on the CodeLab competition page. We also provided weather data for a number of substations in the area to make it easier to use weather in the modeling. And allowed kind of other open data sets as well. So if people had other open data sets that they thought would be useful, they could mention them, and people on the whole competition could use them. We had some really great submissions coming out of this, and so we're going to have talks from the top 3 being shown today. And so kind of in first place was David Evans, and then we had Makadi and Sanjeev kind of coming in third. So we're going to go in reverse order, and we're going to have Sanjeev come and tell us a bit about how he solved this problem. So Sanjeev Kumar is the chief data scientist from Orxagrid and has over 24 years experience in data science, analytics, automation, and AI. So Sanjeev, I'll stop sharing my slides. If you want to turn on your camera and your mic and start sharing your own, that would be great.
Yeah, thanks, Sam. Okay. Okay.
Great, we can see those.
Good morning, and maybe worldwide, if somebody is watching, it could be good afternoon or good evening. Okay. So I'll be covering how I approach this problem. Okay. Just to give you an overview, already Sam has covered something in the overview that, but what I'm looking at it is more on with respect to the data itself. So the complexity is that we had over 40,000 records of training data with the file size of 12 MB, this was the most complex problem when compared to the other two. Then about 40 different substation at different hierarchical level, which is all Sam had mentioned about grid supply point and bulk supply points, and over 4,500 test data missing in various combinations. And apart from that, we had 9 weather stations, which is close to the substations. Okay. So my approach was that since I was looking at what is the best strategy to actually approach this problem. One way is to do the bottom-up approach where you can estimate the or predict the primary substation values and then go up by for the connected BSP, you can just sum it up. But it was clearly mentioned in the contest that the summation is not the possible because some of the values may be missing and some losses. So what I thought is that I was just thinking that instead of looking at the entire hierarchy, why can't you look at each substation as a separate entity? So that's how I approached the problem. I just looked at all the 40 different columns or 40 different substations as separate entity, and the model was built for each column of substation data. So what I did is, in a simple term, if you say take the data of each column, then you will have train data and test data. The test data is any missing values others that will automatically become the test data, and the remaining values of the 2 years data we have will become the train data. So this process, the process of model building was repeated until all the 40 substations were covered. Okay. In terms of the pre-processing, because this is very important whenever you start model building, so you do the pre-processing. So I just use an outlier using box plot. I think this is one common statistical way you treat the missing values. If either you can remove the missing values or you can replace it. So I used the replacement with the most appropriate value. You can kind of estimate it. And with respect to the weather stations, okay, the challenge was that it was not clear that which weather station had the maximum influence on which substation data. So instead of looking at that and building the model and identifying which has the maximum influence, I thought that why can't we merge all the weather station data? So what I did is I merged all the weather station data, and all this was passed as a feature input to the model. Okay. And with respect to the feature engineering, normally in a time series model, you have the day, month, week, and these week of month, week of year. This is seasons, different parts of the data, data, morning, afternoon. So this is a common approach. Okay. But when I actually built the model, this only produced a marginal improvement in the score. So we had a benchmark score of 1. So there was only a marginal improvement. Then I was looking at the various ways to improve the model score. Then I could find a package available, luckily, in our where it automatically extracts features, time series features. In fact, it was extracting 29 features. When I did manually, I could extract about 10 features which had the influence, but this could extract 29 features. So some of the features I will let you know. The approach could improve the score as much as 15%. So that was quite high. From a close of 1, I could come close to 0.8 score. And also all the weather station data was used for model building. In terms of the algorithm itself, I tried to use XGBoost. I think this is the most common and which normally produces very good score. So the model will have the training and validation for each substation. Okay, region was this was the most popular choice of many Kaggle winners and always produced best scores even when you compare to the neural networks. So in terms of the SAS data split up to 80% trained data and 20% validation data. And the model was measured using RMPSC like root mean, percentage square error, and also metrics like MAPE. Okay, the target was minimizing the score. That was our objective. Okay. In terms of the model submission, the final part is that what was done is that model when you build each substation data, after building the model and training, and the model the best score model is chosen, and then the missing values are predicted, and the missing values are merged with the submission data, and the process was repeated until all the 40 different substations were covered. It took almost like 1.5 hours to complete the final submission. Everything was automated. I'll also say something about the visualization slides because I had this as a part of the supporting document. Um, okay. You can see. So this PDF will be generated automatically for each substation. So I can once the model is run, then I can look at it. So this is the sample demand data. Okay. So what was there? And this is the train data. In training, I could achieve about less than 1.5% for most of the substation. Of course, some substation there were some peaks where it could go up to 5% also, or slightly higher. So this just training and predicted values. But what is important is the other part. Okay, so here is the feature important. So these are so 29 features plus you had about 45 different there were 9 weather stations, and each had 5 different features. So now we had 45 plus 29, close to about 30 plus 40, about 75 to 80 odd features. Okay. And some of the features are the week ISO, day, hours 12, index number, AM, PM, weekday, temperature, and so on. Okay. But in your model chooses the most appropriate ones, the top ones are chosen automatically. And here you have the actual versus predicted. This is the value is actually in the unit of watt, megawatt, or whatever is it. And then you can see that the errors are perfectly normalized. So the prediction looks good. And also this is the normality plot. And finally, this is the prediction for test data. Of course, since it is showing like this because the data is not continuous. If the data is, if the missing values are continuous, you would get a proper curve. So that's it from my side. I hope I covered within the 10 minutes time. Any questions?
Great, thank you very much, Sanjeev. So I've got a couple of questions in the chat.
Yeah.
So David Orr's asking, I assume parameters of normality were also used. How were these derived, or did the packages used for historic data incorporate them?
Okay, see, basically I use the R statistical programming, and R statistical package provides a histogram. Okay, this is a function return. Okay, to calculate the histogram. Okay, histogram. So I had a pre-built XGBoost model, so which was also used in the other predictions in our day-to-day work where I work. And this particular test for normality is done using the normality package available in R. Because it's a matter of actually you have excellent packages available. It's a matter of pulling the right package which will suit your need. Yeah.
Great, thanks. I think that leads on to the second question, which I think Steve is asking about the package that you used for feature extraction. What was the name of that package again?
Yeah,
what sort of features does it extract?
Yeah. Actually, the name of the package is recipe. This was the first time I applied the package. Earlier, I used to use normal extraction from the time series, like week of the month, day of the week, and week of the year, and so on. Okay, hours, minutes. Okay, and then time slots and all. Okay, but I by chance I could, when googling and trying to find out, I could find out there's a recipe package available which automatically generates actually 29 features, which can also be extrapolated for 500 odd features. But when I use 500 odd features, I didn't see any improvement in the score. But when I use 29 features from the manually generated features, the score improved as much as 10 to 15%. That is close to 1. It went up to 0.84. So that was a big jump.
And so do you know what kind of features those were that were being
Those
called?
are some of the features. It's here, like daytime, yesterday, whether it was yesterday, then IOC time, 12-hour time, index number, AM, PM, daytime. All these daytime are the features. I can share this also. Daytime, quarter, daytime, weekday, and so on. So wherever daytime is existing, so those are the features which are 29 features, daytime, week 3, whether it is week 4, week 1. Okay, so and so
Great.
on. Yeah.
Another couple of questions. So when you were using XGBoost, did you use a kind of grid search methodology for getting the best hyperparameters? How did you approach that?
Okay, good question. So normally, as I said, that forecasting is forecasting or prediction models. We also often use in our company Oxogrid. Okay, it's over a period of time I have tried to master the right tuning parameters. Okay. So what I have is because if you can reduce the you can increase the number of cycles, but normally it doesn't actually improve the score. So it's a matter of optimum values choosing with respect to how many, what is the depth you can go, and then what is the number of iterations and when you want to stop, and so on. So I would say it's also through an experience of working in the company and also building other models. Yeah.
Okay, so you manually kind of tuned those.
Yeah, it's yes, right.
Okay, great. Thank you very much. That's
You're
really
welcome.
interesting to hear. We'll kind of move on to the next speaker.
Yeah, thank you.
So the second place speaker is from Team Stark, which Matthew Caddy and Jonathan Dennis, who are members of Stark Software, an accredited data collector for electricity metering and experts in energy data analytics. So Jonathan, if you want to share your slides and tell us how you did it.
Yeah, thanks Sam for that introduction. I'll share my slides. Let me know if you can see that.
Yeah.
Excellent. So yeah, I'll obviously be running through. So our entry is coming from Stark, a data science team here at Stark. It's outlined what I'm going to run through. Just give you a bit of a background motivation, because some of you may have heard of us, some of you may have not, but we are a player in the energy industry. So I'll just give you a little bit of a background. Talk through our data exploration, different approaches that we had to the problem, and then we'll give you some details about the models that we used, the results, and what we would have done, like given more time in retrospect. So just briefly, sort of intro about the Stark Group. Actually, a collection of companies. There's Stark that does data collection analytics. We have a field force that does field services and installations, a financing solution, and a gas installer. Like we do a lot of work from like end to end in the data collection, installation, metering part of the industry. So Stark in particular, Stark Data Services, is all about metering data and analytics. We're a half-hourly accredited data collector, data aggregator. Also in the non-half-hourly space, we have meter operator services. We provide gas meter asset management and AMR service provider in gas. That means we collect a lot of energy data. We aim to collect it from any meter or any utility, and aim to strive to be #1 for data quality in the industry. So that gives a lot of data that we want to provide back to our customers, which are typically industrial and commercial customers. We want to empower them to make better decisions, change their behavior, reduce waste, and deliver carbon and financial savings. So the data science team here at Stark is doing that through enhancing the analytics that we provide in our Stark ID platform and providing AI-driven modeling. So it's this competition that WPD is running is right up our street, basically. So I'll just go on and talk a little bit about the data exploration that we did. So initially we've got the substation lists and the information we have from WPD, so we can get our assets labeled correctly. We did a little bit of amalgamation on the weather data to bring together the wind speed data into one vector, and joining the weather data on the closest Euclidean distance to the different locations. So yeah, working with a reasonably large data set, 2 years of demand data, 94 days removed for the purpose of the competition, at least in phase 1. And then we got 1 GSP, 9 BSPs, and 30 primaries, which we can look at and visualize as well on our map. So in terms of our data exploration, we wanted to first sort of observe that hierarchical relationship. This is an example plot of the GSP totaled up against the sum of the BSPs. and you can see that it's close to the sum of the BSPs. So there's a few outliers, as we expected from the description of the competition. But actually, the GSP total is dark blue line here, but it's slightly less than the sum of the BSPs, which is interesting. We did also have a look at the relationship of the BSPs to its primaries. Only one had a particularly strong hierarchical relationship with its child meters. So I guess that sort of underlines the real world nature of this problem. It's, you know, potentially unlike other hierarchical problems where you've got this, other bits of energy being used here and there and are not accounted for in the metering. Another observation we had was around the supply switching, again mentioned, but interesting to observe, where particularly, you know, potentially these meters have a relationship where you can see the demand increasing in one and decreasing in the other. So not a fixed relationship in that hierarchy. Again, very interesting aspect to consider in terms of the data that we're given. So yeah, talk through some of our approaches to the problem. We had three main approaches. I'll just give a quick overview of them and then go a little bit more detail on the one that we submitted as part of the competition. So the first one, we wanted to try a single random forest regression model for the whole data set. So for that, we were feeding in some like meta features about the particular meter that a data point was associated with. So its BSP group, also parent and child demand, some daytime features in the weather, so that the model would be able to learn implicitly that hierarchy by giving it the information about the demand. And the target for that random forest regression model was to predict the meter's demand, all of the meter's demand. So we envisioned that would work for like in particular scenarios. It wouldn't work where the scenarios where we were missing parent and child demand, but one that we wanted to explore because there's advantages to having single models versus multiple models, particularly when you're working with hundreds of thousands of meters like we are here at Stark. So that was our first approach. I will talk through the next one. We also explored a toolkit called scikit HTS, standing for Hierarchical Time Series, something that's available for Python. It's based on forecasting. There's different techniques, but for example, it uses Facebook's Prophet forecasting library for making forward-looking predictions, and then it combines it by work by Hinman on forecasting principles and practice, a method to deal with a hierarchical problem. So you can create the hierarchy as a kind of a map, a dictionary in the code. So that hierarchical structure is incorporated into the model, which is kind of interesting, and you know, there's pros and cons about doing that. It's off the shelf, so something we could just try and learn, not something we'd applied previously to this challenge. But one con to it is that it doesn't really allow for this inflexible hierarchy. It can't handle the load switching or the losses very well. And we didn't have enough time. We might look to extend in the future, I'll mention later, but we didn't integrate our own demand forecasting into it, so we were using the ones off the shelf. Yeah, an interesting package worth mentioning, and have a look at if you're interested in this kind of hierarchical problem. Approach 3 is the one that we did submit. This is a per meter random forest regression model, feeding in lead and lag demand as important features, daytime weather features, of course, and just targeting that single meter's demand. So this is an example of one particular missing day for one particular meter. Our model is predicting the yellow line in the middle for each of the days, and it's got an upper and lower bound demand which we can visualize. So advantage of this approach is that it uses the high-performing random forest regression modeling system that we've built here at Stark, suitable for all the missing data scenarios because it doesn't require any hierarchy. But particularly, it's sort of an extension of the work we've done previously in like getting our analytical modeling into Stark ID. So I like framing it as something that's very close to what we're familiar with. But a big con is that it doesn't include any hierarchical features. Again, I'll talk about that for what we were doing like with a little bit more time. But essentially, we went with approach 3. We found that of the 3 that produced the best results and the most predictable. Others potentially had trouble dealing with outliers and the hierarchical structure in a very good way, at least. So some specific details on the approach that we did. We created an individual time series model for each of the missing days in the the challenge. So that, 94 days, 94 models trained, and those predictions were coming out of each of those models separately. We took a window of time around the missing day to train the model. You could imagine that it'd be training regularly over time, but for the purpose of the competition, we can just focus on the missing days. So we went 90 days back and 30 days forward in terms of our window for getting leads and lags. We had a random forest regressor, as I mentioned. There's a few parameters which we could do tuning on. The best parameters we had were a minimum leaf size of 3 samples, maximum depth set to 20, so we can have a nice specific and not too smoothed out model. And as you probably those be aware, with the random forest, a large number of estimators prevents it from overfitting and gives good result. So we had that set to 100, which was more than sufficient. Feature list, we had date down features that one-hot encoded, weather parameters which we fed in the raw half-hourlies, and then the leads and lags. So back day -1 to day -6, +1, +2, week lags, and a rolling average. So that's what we fed in. What we got out, we got an individual model for each scenario, so we could see the performance. In many cases, we got a good R2 score coming out. For example, the GSP is 0.86, not bad. The average of the BSPs and primaries is also in a similar ballpark. Did vary based on how predictable it was based on its history for each of those models. We could see that for many of the cases, this is just one in particular one that I picked out. The strongest features that the random forest was using were typically day leads and lags. So here's the plot of feature importance for this particular model. The day -1 demand and the day +1 are the most important features, followed by day +2, and then irradiance. So interesting that there is some use of the weather data in the model. It is affecting the the demand at that particular substation. Yeah, and so finally, just to finish up, like if we were given, or if we had a little bit more time and we were to focus on it a bit more, we would have included some hierarchical features, of course. Some of the scenarios would allow for parent and child demand values and their plus or minus leads and lags to be incorporated, so we would do that. And we would look to adapt and improve that HTS package to use our own predictions and to be able to perhaps adjust based on the parent and child assignment at a particular time, because it was sort of varying over time. So this is what we do with a bit more time. And that's it. Thank you very much. Contact details I put up if there are any questions that want to come through by email after this, then happy to answer. Otherwise,
Great.
Yeah, any questions now? I'll answer. Yeah.
I guess the question that we've got in the chat is you use the same hyperparameters for all of the different substations. Did you consider using different ones for different substations? And if not, why not?
Yeah, it's an interesting question. We did use the same one. Partly for time, partly about our model training pipeline. It was easier to kind of support a single set of parameters. But no, it is a very good point. Yeah.
Great, thank you very much. All right. Well, we will now move on to the first place. So we have David Evans, who is a senior engineer for vehicle efficiency attributes at Jaguar Land Rover. So congratulations, David, for winning the challenge, and do tell us how you did it.
Yes, thank you. So I'll jump straight in. I've only really started learning to use Python in the last 12 months, and probably starting modeling around with data science applications the last 6 months. There's been a bit of a push within Jaguar Land Rover to really go all out at developing out big data and data science capabilities, and I felt like I wanted to get involved in that. So this is sort of why I've approached this. So going straight into how I approach the tasks, that's very similar to how Matt and John had done it, as approached it as 94 different sites that I need to predict, splitting out the scenarios by into essentially 14 rather than the initial 8, just based on all the dates. And then a lot of this I felt was more of a challenge for me, was generating a suitable set of Python code to loop each of the scenarios and each of the sites quickly and efficiently, and then be able to then apply models to each of the data sets once I got that initial model working. So what I first did was just simplify it. So for my code, I knew all the sites, just giving them a reference number and name, so it made it a lot easier to keep track of what's going on in all of the code. But so my starting model was start with loop each of the scenarios, get rid of anything where there's missing data or it's known in that scenario that the rest of the data is blank, and then drop everything that's irrelevant, then train the model, train with a random forest to begin with, and then visualize that for each of the sites, so I can get an idea of how visually accurate it looks, but also how score it on the accuracy of the real data. I ended up starting proper with once phase 2 had started, so I was using the phase 1 example data as a good benchmark for me. But my initial starting assumption was basically do nothing with the data, don't even apply plus or minus, look forward or look ahead, and then run that, get that working, and then build upon it from there, which I moved towards adding forward and backwards by 24 hours, assigning day numbers, looking at adding the weather data, and just visually looking at the GPS data for where the weather stations were and where all the other sites were. I concluded that just picking weather station 8 was the best starting point. And based on the previous challenges, I'd found looking forward and back a couple of hours was at least a good starting point for projecting where the weather was, how the weather was influencing the data. And then the key thing for me was just one single data input sheet for everything, where I just put flags across each of the sites to know which scenarios I could ignore and which I could use for when I was running through each of the models. One example of my initial steps of when I was predicting the profiles for for things, I found that it was getting a good predictions across most hours of the day, but getting these really bad predictions in this red shaded area. And it turned out I'd forgotten to add day number to the data, and adding day number really pulled that data much closer in, because particularly for one of the first scenarios, it was a Monday and it was after New Year, and there was a higher startup rate of energy usage across a lot of the sites, meaning this just adding in day number really helped bring in the accuracy for a lot of the models. I then looked at different approaches of which of the models I could try, different random forest combinations, k-neighbors and linear regression as well, and tried a few different things. You can see some various attempts on just the initial main site, and I was struggling to get the KN or the linear regression to get close to at least the shape of the random forests. So I carried on and focused on the random forest as my main approach. I then did a bit of searching and trying to find ways to tune the settings for the random forest to try and get better results. I'd used a bit of code from the site I've linked, where I put some of the input data into that, and it came up with a suggestion of the sample splits of 12, minimal leaf of 5, and max depth of 100. As part of that, I was essentially filling in all the data for each, or using every feature in the initial model generation, and then visually seeing how many of the features were classed as important, and for the majority of the time it was the own sites forward and reverse 24-hour with a big impact, along with the weak numbers. And what I then tried is, once it had found a set of relevant feature codes, I then dropped all the features that were of low importance, less than probably about, I think about 0.5% on off the top of my head, and then rerun it. But I did find that that wasn't yielding an improvement for the majority of sites, and I just left for my final approach. I never needed to drop off any of the features. So just looking at what submissions I did do, my initial one was just raw data with no looking forward and back. I didn't beat the benchmark, but then my second proper submission was just adding in the forward and backwards 1 hour, adding the day numbers, and just with 240 estimators, I achieved the best results. I tried adding it with the weather and also a number of different estimators. I found the weather data didn't help. And then my final attempt was, for the few sites that I did find that there were improvements by dropping numbers of features, I reran it again, but it was a very small, it was a small improvement over the weather approach, but it didn't get close enough to the original third submission, which in the end, weather didn't have any impact for my winning model, and it was just a case of looking forward and back 24 hours. Finally, so conclusions, I definitely did not do enough data cleaning. It was essentially, most of my time was focusing trying to get the model to loop and work properly. There was definitely scope for tuning my models on a case-by-case basis, or might have potentially had a different model for each of the 94 different scenarios. So if I had the time and definitely the skill to try and do that investigation, I would have, I think I'd certainly include that in the initial loop and investigations to try and understand how big of an impact changing the model approach per site would have done. And that's it for me. Thank you.
Great, thanks very much, David. So got a few questions in the chat. So did you apply cross-validation when comparing the random forest performances, or just refer only to the kind of training and the preliminary data from the first phase?
It was mostly, yeah, so it was really just comparing to the first phase data. I was, for the second phase data, I was doing a 80-20 split of the data to try and help drive the model direction, because that at least gave me an idea of if I needed to drop features, or if dropping features would work or not for the phase 2.
Yeah, that makes sense. And the kind of visual inspection of the model kind of gave you some good insights, but obviously that's quite difficult to scale up to a really large number of substations. From kind of learning from those insights, do you think there are particular metrics or another non-visual way that could like achieve a similar goal? Any thoughts?
Yeah, definitely. I, as well as the visual, I was doing there's essentially an R-squared calculation of accuracy for each of the sites, and when it was going below circa, most of the good ones were in the 95+%, but the ones I'd focused then on the ones that were going, some of them were dropping to 70-60%, where it's just completely, it seemed in a lot of the cases just completely random noise compared to the good sites. But yes, that was, I'm sure there's plenty of other ways to do it.
For a question from me is, for phase 2, did you basically apply the same models as you did in phase 1, or did you kind of do a lot of rework on trying to get them working on phase 2?
No, it was just everything I used on phase 1 training, it was just for phase 2. So there's nothing apart from the addition of the phase 1 data in the data set. There was no other difference.
Yeah. Okay, great. And then we've got a question which is a request, which is, could you put that link up to the random forest walkthrough that you mentioned? If you could just pop that in the chat, people would find that helpful as well.
Yep, thank you.
Great, thanks very much, David. So Steve, it's over to you. Let me share the slides.
Brilliant, thank you very much. Thanks to all the speakers as well. That's brilliant. So I'm just going to really wrap up the what we've done in this series, really, what lessons we've learnt and and what outcomes have come. So we go to the next slide. Just a kind of quick summary, really, of what we've achieved with these challenges. So we've run 3 challenges, which we hope really focus on, are very adjacent to sort of those really facing network operators and DNOs. The first one was sort of trying to reduce monitoring sizes. The second one, looking at a major problem where networks have to deal with, the new low carbon technologies, which will be putting increased strain on the network. And of course, the missing data one, which you've all just seen. What's been great for us has been, we've been able to, via these challenges, release some very interesting, unique data sets, but with a lot of other information with them, and I'll get into that in a later slide. But we've been really pleased with the engagement. So there's been really enthusiasm for dealing with this data, and I know a lot of people who are keen to use this data, following on from these challenges as well. As Liam mentioned at the start, there's the idea we can develop sort of competitive benchmarks, and from every one of these challenges, we've noticed that the scores, as you can kind of see on the right one there, from you can see phase 1 and phase 2, you start converging to sort of an optimal solution, or at the very least, we're reaching a sort of local optimal solution, shall we say. So we're developing things which are really good baselines for people to get involved in these fields. You can understand what maybe is a good starting place, or maybe even a competitive benchmark to compare your own methods to. So we really hope it can be used to sort of develop further research and let new innovators or current innovators enter into different areas and develop these things. And there's been a lot of publication of knowledge and tools, which I'll also get to later. The other learning, of course, is the data science. We've seen throughout these challenges a variety of models used. We've just seen quite a lot of cool ensemble methods being applied, but everyone's tried lots of different things. So we're getting a good idea of what sort of things might work. But they've also demonstrated techniques which haven't necessarily been demonstrated in sort of this comparison environment, techniques such as model combination, which are again and again shown as very effective ways to take the models you currently have and making an improved model, say, by bringing them together. It's also the way people are using data. So there's been quite a few cases where we've seen there's been an improvement by using other data sources, so linking them together to get extra value. Weather is one of those, but we've also had people using national level data and other things to try and improve their solutions. And also some novel and uncommon feature engineering methods as well. So how people deal with, for instance, exponential smoothing methods had been applied to sort of the temperature data. Next slide, please. Yeah, I mentioned about the unique data sets. So I've just put a couple of the main data sets on there from on 2 of the challenges. So we had the high resolution data. We're very pleased to get a minute level data out for the first challenge. Very effective, and we know people have used that and we're going to continue to use that. And also the hierarchical demand data. There's very few examples of hierarchical demand data out there, and also having that connectivity information. So it's not just about the demand data, but there's a whole host of other supplementary information, like the location, the distributed generation, which is connected to it, some of the capacities. And also we've included things like the numbers and the types of consumers with a few of the challenges. So we're really pleased with these unique data sets being out there, and we hope they will help to drive some innovation in the area. Next slide, please. The other thing I mentioned was participation. We think there's been a big interest in these challenges. You know, the kickoff events have had hundreds of people attend, and then further hundreds of people have watched these things online. So we're very pleased with that. And you know, people are really engaging with these challenges. They're spending a long time working on them. You know, I know people are very busy, but you know, it's shown that there is, you know, when there's unique data sets are released out there within, you know, a certain environment, then people are very keen to use them. We had a LinkedIn group, which was from the previous challenge, which had 120 members. And since we ran these challenges, we've now tripled that. So we've got over 360 now LinkedIn members on that group. I'd advise anyone to join that as well, because we share lots of things on there, very interesting stuff. But also, you know, it's not, people aren't just necessarily, some people aren't engaging with the challenge, they don't have time to do it, but the data itself is showing a lot of interest. So the data hub page, which has all the challenges on, has had over about 2,000 page views, and the data itself has had 1,000 downloads. So half of the people viewing that data are downloading it. And we already know people are thinking of using them for research projects, or maybe helping train students with certain methods by using that data as well. And yeah, so there's a lot of engagement as well. Over 2,500 submissions across these challenges, and we've had at least 37 teams who've engaged. Next slide, please. As I say, there's been a lot of outcomes as well. We're really pleased, and these are the ones we know about. If anyone starts using the data for other things, then we really want to hear about it. There is already one paper under review, which is based on these challenges. That was the winning team from the first challenge. We've had people sharing code, so there's at least 2 teams who've shared codes from the challenges, so people can pick that up and you know, have a head start with developing their methods and doing some feature extraction or visualizations. And we've also had some individuals creating some tools. So we had a visualization prize for challenge 2, and the second place team created a really snazzy visualization tool part of that. But of course, you know, we're all learning about the methods that are applied. Just like today, we've had you know, we'll be releasing that later on our YouTube page, but you know, we've had a lot of engagement on those channels, and people can learn about the various methods that are applied, you know, from the winning teams as well. So we know they're good quality. So I just want to wrap up. We go to the final slide. You know, what we are doing now is we're going to be sort of wrapping a lot of this up here. We're going to compile all the learnings we've got from it. You know, there's still a lot of potential things we could do, so we'll be discussing that in the next you know, few weeks and a month or so. We want to track those impacts. So if you've used this data in any way, then please let us know. But there's a lot of things we could have done, and you know, either time constraints or you know, resource constraints meant we couldn't try everything. But there's so many things we could do here, and we think there's a lot more value perhaps by looking at different ways of doing this. So I think my slides are moving around. Yeah, so code submissions is one we really maybe want to try out. You know, we've been doing result submissions, so we can do something a bit more real time, perhaps, if we look at something like code submissions. Longer timeframes could be useful for other types of challenges, of course. These are very short challenges. The pod one was slightly longer, and you get different sort of interactions and usages of the data and different problems. And finally, we could do different data sets. We've mainly focused on sort of demand time series because, you know, it's a fundamental element of distribution network operators and energy sector in general. But there's obviously a lot more out there we could do, perhaps image data sets or even social media data and that sort of thing. So, you know, we're hoping that these have demonstrated, you know, what competitions are useful for, what the value is in the data, you know, and we hope there's been a lot of learning and you know, improved participation and a building of the community really from these things. So I just want to finish with thanking everybody who's been involved in this challenge. You know, obviously the participants are the main thing that make these things really, really good. And I think we've had a great engagement. We've had some brilliant methods applied, but also thank you to the WPD team who worked so hard with us to get that data released and help engage people through the use of their really incredible data. So I want to thank everyone on the team for that. I'm happy to take any further questions we have on that, but my finishing remark will be that we hope there's a lot more we can do here, and we hope that, you know, people will be engaged. And if you have any interesting ideas, then please share them with us.
All right, thank you, everybody. If there aren't any more questions, then that's it. Please do join the LinkedIn group, and we'll post, if there are future challenges coming up, we will post the details there. Thank you, everybody.
I'll put the LinkedIn group in the chat as well if anyone's interested in joining that. So